In this podcast, we'll be looking over hybrid orbital theory. Some chemists think of hybrid orbital theory as an extension of valence bond theory. If you recall from the last podcast, the valence bond theory was very successful in explaining chemical bonding in terms of bond strength and overlap of atomic orbitals. However, it did not explain bonding in terms of SP-DF orbitals, which is our current quantum mechanical model of atom. Hybrid orbital theory takes the concept of overlapping of atomic orbital and explains it in terms of SP-DF orbitals, which is our current quantum mechanical model. The hybrid orbital theory's basic assumption is that atomic orbitals that are present in atoms are very different than the orbitals that take place that are involved in bonding. So every atom must undergo some changes before it can actually bond, and this change in atomic orbitals is called as hybridization. And as you know, this term hybrid or hybridization means mixing, forming of something new in between, and that's exactly the context this term is used in this podcast. So there are atomic orbitals SP-DF as suggested by a quantum mechanical model, and before the atom can bond, the central atom's atomic orbitals SP-DF undergo hybridization or mixing to form hybrid orbitals, and these hybrid orbitals could be sp orbitals, sp2 orbitals, sp3 orbitals, sp3d orbitals, or sp3d2 orbitals. I would suggest that you go on the animations of hybrid orbitals and watch the hybridization movie. These are both great links. Now, hybrid orbital theory has two main key points. The first key point here is that number of hybrid orbitals obtained by mixing of atomic orbitals is the same. So if you mix two atomic orbitals, one s and one p, you will get two hybrid orbitals. The second is the type of hybrid orbitals or their nature. What would their shape be? What would their characteristic be? Depends on how many and what type of atomic orbitals are being mixed. If you have a sp hybrid orbital, because it has s and p character equally, the hybrid orbital shape will be that of between s and p. Versus if you have a SP3 hybrid orbital where you have one s and three p orbitals mixing, it'll have a little bit more of p character than the s, and the sp3 hybrid orbitals will look more like a p orbital than a s, because there are three p orbitals mixing for one s orbital. Now, what are different types of hybrid orbitals? Let's start with the sp hybrid orbitals. Sp hybrid orbitals are formed when one s and one p atomic orbital mix, and the s orbital shape, as you know, is spherical, and the p orbital shape is dumbbell shaped. And because they are mixing in a 1-to-1 ratio, the sp hybrid orbitals are little less circular than s, but little bit more rounded than the p. So by mixing of one s and one p hybrid orbital, you form two sp hybrid orbital. So one s and one p atomic orbital mix to form two sp hybrid orbitals. And these two sp hybrid orbitals, they lay 180 degrees apart from each other to be farthest from each other. So hybrid orbital theory takes into account the VSEPR theory as well, where it says that the electron domains will tend to be as far apart from each other as possible. And now I'm going to move on to SP2 hybrid orbital, and you can see how the sp hybrid orbitals are arranged in case of beryllium fluoride molecule. sp2 hybrid orbitals are made when you have one s and two of the p orbitals mixing. sp2 hybrid orbitals are a little bit fatter or more rounded than the p orbitals, and because one s and two p orbitals are mixing, you get three SP2 hybrid orbitals, and you can see it's not quite as spherical as S, but it's not as thin as P, so the shape is in between the two, and the shape is more like a radiation sign. And because there are three orbitals here, they tend to be at 120 degrees from each other, trigonal planar arrangement. And you can see how BF3 molecule is formed here by overlap of SP2 hybrid orbitals. Now let's go to SP3 hybrid orbitals. In SP3 hybrid orbitals, you have one s and the three p orbitals mixing, px, py, and pz. And what you get is tetrahedral arrangement of SP3 hybrid orbitals. There are four SP3 hybrid orbitals formed. Because you're mixing four orbitals, you get four, and each of them are arranged at angle of 109.5 degrees, and the shape is tetrahedral. SP3D are trigonal bipyramidal, and SP3D2 are octahedral. Now, the non-bonding or lone pairs occupy hybrid orbitals too. So if you have a lone pair, that can occupy a hybrid orbital. And now the big question is, and I'm going to add here, if you have any molecule, let's say water molecule, and you wanted to predict what's the hybridization on the central atom. I want to clarify one thing. Hybridization is used in context of the central atom only. The side atoms orbitals do not undergo hybridization. It's only the central atoms atomic orbitals that undergo hybridization. It's almost like thinking that the central atom is acting like a host, where the side atoms are acting like a guest. They are coming and sharing the electrons, but the central atom is the one that needs to undergo changes to accommodate these incoming electrons. So to be able to predict hybridization, first you write what type of ABE molecule it is. In water, when you draw its Lewis structure, you know it's AB2E2 molecule. Now A is the central atom, so you can ignore A. Now see how many bonded and lone pairs are present. There are two bonded and two lone pairs are present. So you need four orbitals in all. Now which hybridization produces four orbitals? SP3 hybridization. That's how you know that the hybridization on the central atom, which is oxygen, is SP3. And if you had to draw these orbitals, how would you draw it? You know oxygen is in the middle, and you know it's a bent structure because of the two lone pairs, as said by VSEPR theory. If you had to draw its hybrid orbitals for oxygen, you will draw SP3, and you know SP3 hybrid orbitals are arranged as a tetrahedron, and two of the orbitals overlap with hydrogen, and you know hydrogen you'll draw spherical. For S, it's unhybridized S, and S is always spherical. Why S? Because hydrogen's valence electron is present in S orbital, and here there'll be two lone pairs. So this will be the structure of water molecule as for hybrid orbital theory. Now if you had to draw C2H6's structure, it's important to understand all of these hydrocarbon structure because they are a little different. In C2H6 there really is no central atom, right? There are two carbons and hydrogens are attached to it. What we think of it is C2H6 being made of two equal halves of CH3. Now if you think of it as two equal halves of CH3, now there is a central atom, right? So around the central carbon, how many bonds are present? 4 bonds. So what should be the hybridization on central atom, which is carbon here? SP3, because there are 4 bonds around it. So you draw SP3 as tetrahedral, right? And then 3 of them have overlapping sigma hydrogen bond. How do you know it's a sigma bond? Because it's a single bond. Every single first bond is always sigma bond, and you'll draw spherical s orbitals for hydrogen because hydrogen's valence electron is present in s. And on the other end, let me just get rid of this. On the other end, you will draw another carbon with a tetrahedral orbitals, and then there will be overlap of 3 hydrogens over here. So this bond here, this bond is represented right here. This bond is formed by a sp3 overlap. This bond is formed by a sp3s overlap. This is formed by sp3s overlap. This is formed by sp3s overlap as well. I recommend that you watch the animation that's in this PowerPoint because it puts it very nicely in the 3D for you to be able to understand this. Now let's go over C2H4 molecule structure. C2H4, how do you draw it? It's C double bond C and then 2 H's, and this is the structure. Again, you'll take half of this molecule. The first thing for you to do is to label your sigma and pi bonds. Okay, remember the second and third bond in a multiple bond situation is always a pi bond. Now sigma bonds, you know, are formed by hybridization, while pi bonds are formed by unhybrid p orbital. So if there are 3 sigma bonds, how many hybrid orbitals are present around the carbon? 3 hybrid orbitals. And which hybridization produces 3 hybrid orbitals? SP2. So you know your central carbon atom has SP2 hybridization. And how do SP2 hybrid orbitals look? They look like this. They are at 120 degrees from each other. And if it is SP2 hybrid orbitals, there is also one unhybridized p orbital because there are 3 p orbitals. In SP2, only 2 of the p orbitals participated. So there is the third one that's unhybridized. Similar thing is happening on the other end. Let me just redraw it. I want to redraw to make it a little bit better. So you have your carbon, so 120 degrees, 1, 2, and 3, right? Similarly, you have another carbon and it has 1, 2, and 3. Each of these is SP2 hybrid orbital. How did we know that the central atom has SP2 hybrid orbital? Because we saw there are 3 sigma bonds around it, and each sigma bond is formed by a hybrid orbital. Now, for each of these carbon, there's also an unhybridized p orbital, and then there is a hydrogen overlapping with these SP2 hybrid orbitals to form this bond. So this bond actually is formed by a sp2s overlap. This bond is formed by sp2 overlap. So what is the bond angle here? If somebody were to ask you between this carbon and carbon, even though we draw it straight, but because it's at 120 degrees, the bond angle is 120. The carbon-carbon bond angle here is 180, but this CH bond angle is 120 because of the sp2 hybridization. And these unhybrid p orbitals overlap to form the pi bond. So this is the structure of C2H4 molecule. So before you can predict the bond angles, you got to look at the hybridization on the central atom, and then you have to see what bond angle is present for those hybrid orbitals. If it is sp2 hybridization, then the bond angle between the hybrid orbitals is 120 degrees. If it were sp3 hybridization, then bond angle will be 109.5 degrees. Now moving on to delocalized versus localized bonds. So whenever there is a double bond present, you know there is a sigma and a pi bond. In some molecules, you see resonance. If you recall, resonance is a phenomenon where there is a traveling double bond, or you can have more than one correct Lewis structures. In case of resonance, the electron density is spread over a larger area. It is not confined to the space between two atoms. Such bonds are called delocalized because they are not localized or confined to the space between two atoms. When the electron density is present over a larger area, it's called delocalized. A delocalized bond is more stable than a localized bond because electron density is spread over a larger area, reducing electron-electron repulsion. The best way to figure out a delocalized bond is to look for resonance. If resonance is present, it's a delocalized bond. So you can see that this is not a delocalized bond because there's no resonance here, but this one is a delocalized bond. The best example is for benzene. So if you remember, benzene is a hexagon with alternating double bonds. That's one structure. In the other structure of benzene, these double bonds travel. So what happens due to the traveling of double bonds or resonance, there is a common area of electron density on top of the carbon-carbon ring and another such area at the bottom of the carbon-carbon ring. These areas are the general electron cloud where electrons are present. So you can see that the electrons are delocalized versus of being localized. The delocalization or resonance makes a molecule more stable. That is the end of this podcast. Thank you for listening.